Welcome to today's episode of Earth's Frozen Chronicles, where we dive deep into the most incredible climate stories our planet has ever witnessed. Imagine looking down at Earth from space and seeing not the familiar blue marble we know today, but a gleaming white ball of ice stretching from pole to pole. Picture oceans locked solid under ice sheets thicker than skyscrapers are tall, and continents buried beneath glaciers that dwarf anything in our modern world. This isn't science fiction, this is Earth's actual history. Multiple times throughout our planet's 4.5 billion year story, our world has transformed into something almost unrecognizable. During these Snowball Earth events, the planet's surface became nearly entirely frozen with no liquid, oceanic, or surface water exposed to the atmosphere. Scientists contend that at least two Snowball Earth glaciations occurred during the Cryogenian period, roughly 640 and 710 million years ago. But perhaps the most remarkable aspect of the last glacial maximum was that it wasn't permanent. This frozen world, which seemed so stable and enduring, was actually poised on the edge of dramatic change. Climate records show that the transition out of the last glacial maximum began around 19,000 years ago and accelerated rapidly around 15,000 years ago. The collapse of the ice sheets was surprisingly rapid. Massive ice sheets that had taken tens of thousands of years to build could disappear in just a few millennia. Past ice sheets have retreated rapidly, raising global sea level at rates 1 centimeter per year, with marine ice sheets collapsing and terrestrial ice sheets retreating in a more gradual fashion. The last glacial maximum reminds us that Earth's normal state isn't necessarily what we experience today. For most of the past 3 million years, conditions like those 21,000 years ago have been more typical than our current warm climate. The ice-covered world of the last glacial maximum was the rule, not the exception, in Earth's recent geological history. Chapter 1. Snowball Earth Picture. Earth as a cosmic snowball, spinning silently through space with every ocean, every sea, every river locked in ice so thick that sunlight barely penetrates its surface. This isn't just another ice age, this is Snowball Earth, perhaps the most extreme climate event our planet has ever experienced. The Snowball Earth hypothesis proposes that during one or more of Earth's Icehouse climates, the planet's surface became nearly entirely frozen with no liquid, oceanic or surface water exposed to the atmosphere. Imagine temperatures so brutal that they reached -58 degrees Fahrenheit, -50 degrees Celsius, cold enough to make Antarctica's harshest winter feel tropical by comparison. Scientists contend that at least two Snowball Earth glaciations occurred during the Cryogenian period roughly 640 and 710 million years ago. Each lasted about 10 million years or so. 10 million years of a frozen planet, a time span so vast that it dwarfs all of recorded human history by thousands of times over. But how does an entire planet freeze solid? The mechanism is both elegant and terrifying. Initial cooling result in an increase in the area of Earth's surface covered by ice and snow, and the additional ice and snow reflect more solar energy back to space, further cooling Earth and further increasing the area covered by ice and snow. This runaway feedback loop is like a cosmic thermostat gone haywire. Once it starts, it's almost impossible to stop. The evidence for this planetary catastrophe lies buried in rocks around the world. The main evidence of the severity of these events comes from geological evidence of glaciers near the equator. Imagine finding evidence of massive glaciers where modern-day Brazil or Central Africa exist today. As one scientist put it, if you can think of continent-size ice sheets sitting where Saudi Arabia is right now, that will give you an idea of how cold the environment seemed to be. These weren't ordinary ice sheets. Computer modeling suggests that a hard snowball would have ice covering the oceans up to 1 kilometer thick. Picture Manhattan skyscrapers buried beneath solid ice, with room to spare. The oceans themselves would have been transformed into something unrecognizable, a frozen wasteland where waves once crashed and marine life once thrived. Yet here's where the story becomes even more remarkable. Some scientists believe that certain life forms did survive. Fossils from this period indicate that tiny organisms such as algae, which need sunlight and open water, lived both before and after the Snowball Earth. How could life possibly endure such conditions? The answer might lie in hidden refuges. Recent research suggests that open water, ice-free conditions existed in mid-latitude oceanic regions during the waning stage of the Marinoan Ice Age. Even in the depths of a global freeze, Earth might have harbored secret pockets of liquid water, tiny oases of life in a frozen desert. But perhaps the most mind-bending aspect of Snowball Earth is how it ended. Global warming associated with large accumulations of carbon dioxide in the atmosphere over millions of years, emitted primarily by volcanic activity, is the proposed trigger for melting a Snowball Earth. Picture volcanoes continuing to belch greenhouse gases into the atmosphere while the planet remains locked in ice. For millions of years, this CO2 would accumulate, since the normal processes that remove it from the atmosphere, like rock weathering, would be halted by the global freeze. The amount of carbon dioxide needed might be several hundred times higher than what our atmosphere contains now. When this atmospheric greenhouse finally reached a tipping point, the thaw would have been dramatic. Due to positive feedback for melting, the eventual melting of the snow and ice covering most of Earth's surface would require as little as a millennium. Imagine Earth transforming from a frozen wasteland to a hothouse in just 1,000 years. When the ice sheet melted under a hot atmosphere rich in carbon dioxide, it would cover the oceans with a layer of warm, 50-degree fresh water up to 2 kilometers thick. The planet would have resembled a giant hot tub, with surface waters hot enough to be uncomfortable to touch. The implications for life were profound. While many refugia have been postulated, global ice cover would certainly have ravaged ecosystems dependent on sunlight. Some scientists think that the conditions of Snowball Earth changed life in the oceans, leading to the rise of more complex algae, large cells, over cyanobacteria, small cells. In a very real sense, the most extreme climate event in Earth's history may have set the stage for the evolution of complex life. Yet debates continue about whether Earth truly froze completely. An alternative theory has developed that goes by the name slush ball. In this case, the Earth becomes largely covered with ice, but open water remains near the equator. Whether hard snowball or slush ball, these events represent climate extremes almost beyond imagination, reminders that our planet is capable of transformations that would make today's climate change seem mild by comparison. The Snowball Earth. Events ended more than 600 million years ago, but their legacy shapes our planet still. They remind us that Earth's climate system can tip into states so extreme that they challenge the very survival of life itself. Chapter 2. From Greenhouse to Icehouse. If Snowball Earth represents the ultimate frozen extreme, the transition from the greenhouse world of the early Cenozoic to our modern icehouse climate tells a different story, one of gradual cooling that fundamentally reshaped our planet over tens of millions of years. 55 million years ago, Earth was almost unrecognizable. The average temperature of Earth at the beginning of the Eocene was about 27 degrees Celsius. Summer high temperatures in Antarctica were around 25 degrees C, 77 degrees. Temperatures during winter were around 10 degrees C, 50 degrees C. It did not frost during the winter. The climate was so warm that trees grew in Antarctica, palm trees swayed in the Arctic, and crocodiles basked in what is now the Canadian High Arctic. This was the Paleocene-Eocene thermal maximum, Earth's most recent experience as a true hothouse planet. Average global temperatures were around 30 degrees C, 86 degrees K. This was only the second time that Earth reached this level of warmth since the Precambrian. The world had no ice sheets, no glaciers, and sea levels were 150 meters higher than today, high enough to submerge most of Florida and turn much of the Amazon into an inland sea. But this greenhouse paradise was destined to end. Around 50 million years ago, Earth entered a period of long-term cooling. This was mainly due to the collision of India with Eurasia, which caused the rise of the Himalayas. The upraised rocks eroded and reacted with CO2 in the air, causing a long-term reduction in the proportion of this greenhouse gas in the atmosphere. The birth of the Himalayas was more than just a geological event, it was a climate revolution. Some scientists believe that the Himalayas are a major factor in the current ice age, because these mountains have increased Earth's total rainfall and therefore the rate at which carbon dioxide is washed out of the atmosphere, decreasing the greenhouse effect. As these mountains rose, they created the world's most effective CO2 scrubbing system, slowly draining the greenhouse gases from Earth's atmosphere. The cooling didn't happen overnight. The evolution of the Eocene climate began with warming after the end of the Paleocene-Eocene thermal maximum at 56 Ma to a maximum during the Eocene optimum at around 49 Ma. For millions of years, Earth oscillated between extremely warm periods and merely very warm ones. But continental drift was reshaping the planet's climate system in fundamental ways. At the beginning of the period, Australia and Antarctica remained connected, and warm equatorial currents may have mixed with colder Antarctic waters, distributing the heat around the planet and keeping global temperatures high. When Australia split from the southern continent around 45 Ma, the warm equatorial currents were routed away from Antarctica. This geological divorce had profound consequences. In the mid-Eocene, the Antarctic circumpolar current between Australia and Antarctica formed. This disrupted ocean currents worldwide and as a result caused a global cooling effect. The birth of this current created the world's most powerful ocean conveyor belt, isolating Antarctica from warm tropical waters and setting the stage for the first ice to form at the South Pole in over 100 million years. The milestone moment came 34 million years ago, the Eocene-Oligocene boundary. 33.9 million years ago was the transition from the last greenhouse period to the present icehouse climate. At this point, when 125% more of Antarctica's surface was above sea level and able to support land-based ice sheets relative to today, CO2 levels had dropped to 750 ppm. Around 35 million years ago, permanent ice began to build up on Antarctica. Picture this momentous event. For the first time in over 100 million years, snow falling on Antarctica didn't melt away during summer. Instead, it accumulated year after year, building into glaciers, then ice sheets, transforming the southernmost continent from a forested, temperate land into the frozen wilderness we know today. The ice didn't stop growing. By 29.2 million years ago, there were 3 ice caps in the high elevations of Antarctica. One ice cap formed in the Dronning Maudland, another ice cap formed in the Gamburtsev mountain range, another ice cap formed in the Transantarctic Mountains. These separate ice caps would eventually merge into the massive East Antarctic ice sheet. By 28.7 million years ago, the Gamburtsev ice cap was now much larger due to the colder climate. The ice was spreading, claiming more and more of the continent. 6 million years after the start of the late Cenozoic Ice Age, the East Antarctic ice sheet had formed, and 14 million years ago, it had reached its current extent. But Antarctica was just the beginning. The cooling trend continued in the Miocene with relatively short, warmer periods. about 15 million years ago, was the warmest part of the late Cenozoic Ice Age, with average global temperatures around 18.4 degrees Celsius. Atmospheric CO2 levels were around 700 ppm. This time period was called the mid-Miocene climatic optimum. Even during this optimum, Earth was far cooler than the greenhouse world of 55 million years ago. The planet had entered a new climate state, an icehouse world where permanent ice existed somewhere on Earth at all times. By 14 million years ago, the Antarctic ice sheets were similar in size and volume to present times. Glaciers were starting to form in the mountains of the northern hemisphere. The transformation of ocean circulation was equally dramatic. When South America became attached to North America, creating the Isthmus of Panama around 2.8 million years ago, the Arctic region cooled due to the strengthening of the Humboldt and Gulf Stream currents. This small strip of land between the Americas fundamentally altered global ocean circulation, creating the modern pattern of currents that helps maintain our current Ice Age climate. The final piece of the puzzle came when ice spread to the northern hemisphere. The glaciation of the Arctic in the northern hemisphere commenced with Greenland becoming increasingly covered by an ice sheet in late Pliocene 2.9–258 Ma ago. For the first time in over 30 million years, both poles were simultaneously covered in permanent ice. This transition from greenhouse to icehouse didn't just change temperatures, it revolutionized life on Earth. The end of the Eocene was marked by the Eocene-Oligocene extinction event, also known as the Grande Coupure. Tropical forests retreated, grasslands expanded, and new types of mammals evolved to thrive in the cooler, drier world. The cooling also intensified Earth's seasonal contrasts. The late Eocene saw the rebirth of seasons, which caused the expansion of savanna-like areas along with the evolution of grasses. For the first time in millions of years, Earth had distinct seasons: winters cold enough for snow, summers that provided respite from the cold. By 3 million years ago, Earth had achieved its modern configuration. By about 3 million years ago, an isthmus had formed between North and South America, joining both continents and preventing oceanic currents to circulate between Pacific and Atlantic oceans. The stage was set for the great ice ages that would define the next chapter of Earth's climate story. This transformation from greenhouse to icehouse took 50 million years, a timescale almost impossible to comprehend. Yet it shows how Earth's climate system can undergo fundamental permanent changes. The warm world of the Eocene is as alien to us as an ice-covered planet, reminding us that what we consider normal climate is actually a brief moment in our planet's long and dramatic climate history. Chapter 3: The Birth of the Modern Ice Ages. 3 million years ago, Earth entered a new phase of its climate story, one defined by rhythmic pulses of ice that would advance and retreat across continents like a planetary heartbeat. This was the beginning of the Quaternary Ice Age, our current Ice Age, which continues to this day and has shaped the world humans would eventually inherit. The LGP is part of a larger sequence of glacial and interglacial periods known as the Quaternary glaciation, which started around 288,000 years ago and is ongoing. The glaciation and the current Quaternary period both began with the formation of the Arctic ice cap. Unlike the gradual cooling that marked the transition from greenhouse to icehouse, the Quaternary Ice Age was characterized by dramatic swings between frigid glacial periods and warmer interglacials. Earth's climate alternates between ice ages and greenhouse periods during which there are no glaciers on the planet. Earth is currently in the ice age called Quaternary glaciation. But this ice age was unlike anything Earth had experienced before. While previous glaciations might affect one hemisphere or region, the Quaternary Ice Age would see massive ice sheets growing simultaneously in both the northern and southern hemispheres. The trigger for these rhythmic climate swings lay in space itself. Over the past few million years, the glacial-interglacial cycles have been paced by periodic variations in the Earth's orbit via Milankovitch cycles. These orbital cycles, changes in Earth's tilt, wobble, and the shape of its orbit around the Sun, created subtle but crucial changes in how much sunlight different parts of Earth received during different seasons. The early Quaternary ice ages were different from what would come later. Initially, glacial cycles lasted about 41,000 years, matching Earth's tilt cycle. But around 900,000 years ago, something fundamental changed. The cycles stretched to approximately 100,000 years, creating longer, more intense glacial periods separated by brief, warm interglacials. Individual pulses of cold climate within an ice age are termed glacial periods. Glacials, glaciations, glacial stages, stadials, stades, or colloquially, ice ages. And intermittent warm periods within an ice age are called interglacials or interstadials. These weren't gradual transitions, they were dramatic climate swings that could transform continents in just a few thousand years. The ice sheets that defined these glacial periods were monsters of almost incomprehensible scale. During peak glacial periods, massive ice sheets covered much of Canada and the northern United States. The Laurentide ice sheet alone stretched from the Atlantic to the Pacific, covering an area larger than the entire contiguous United States and reaching thicknesses of over 2 miles in some places, tall enough to bury modern skyscrapers with room to spare. In Europe, the Fennoscandian ice sheet blanketed Scandinavia, much of northern Germany, and extended into what is now Russia. Britain was buried under ice thick enough to completely obliterate its landscape, creating a frozen wasteland where London would one day stand. In the northern hemisphere, the northern third of North America was covered by the Laurentide Cordilleran, and Greenland ice sheets and other ice sheets blanketed many European regions, including Scandinavia, the British Isles, and parts of northeastern Europe and north-central Siberia. These ice sheets didn't just sit passively on the landscape, they were dynamic, flowing rivers of ice that carved and sculpted the continents. They gouged out the Great Lakes, carved Norwegian fjords, and created the thousands of lakes that dot Canada and Scandinavia. The weight of the ice was so immense that it literally depressed the Earth's crust, pushing the solid ground down by hundreds of meters. But the most dramatic impact was on the oceans themselves. The massive sheets of ice locked away water, lowering the sea level, exposing continental shelves, joining land masses together, and creating extensive coastal plains. During peak glacial periods, sea levels were approximately 125 meters, 410 feet, lower than those of the present day. Picture the implications. Vast areas that are now underwater were dry land. Land bridges connected several regions now separated by ocean. Japan was linked to mainland Asia in 2 locations. Australia, Tasmania, and New Guinea were joined to form the continent Sahul, and northeastern Asia and northwestern North America were connected to each other by the Bering Land Bridge. The English Channel was a river valley. The North Sea was largely dry land where early humans hunted mammoth and reindeer. Another land bridge connected the island of Great Britain with the rest of continental Europe. The island of Ireland is in turn connected to Great Britain by a giant ice sheet. What we now call the British Isles was actually a peninsula of continental Europe. In Asia, the geography was equally transformed. In Japan, the low water level made the Sea of Japan a lake, and a land bridge connected the region to the Asian mainland. The Yellow Sea, famous as a modern-day fishing location, was completely dry. Ancient humans and animals could walk from Korea to Japan, and vast grasslands stretched where productive fishing grounds exist today. The atmospheric effects were equally dramatic. The ice sheets also changed the atmospheric circulation, causing the northern Pacific and Atlantic Oceans to cool and produce more clouds, which amplified the global cooling as the clouds reflected even more sunlight. The average global temperature about 21,000 years ago was about 6 degrees C, 11 degrees colder than today. This wasn't just a matter of cooler summers and colder winters. It was a fundamental reorganization of Earth's climate system. During the last glacial maximum, much of the world was cold, dry, and inhospitable, with frequent storms and a dust-laden atmosphere. The dustiness of the atmosphere is a prominent feature in ice cores. Dust levels were as much as 20 to 25 times greater than they are in the present. The dust came from expanded deserts and reduced vegetation coverage. With so much water locked up in ice, many regions became arid wastelands. The dry climate during the last ice age brought about the expansion of deserts and the disappearance of rivers, but some areas saw increased precipitation from falling temperatures. The world resembled a vast dusty tundra, punctuated by massive ice sheets and small refuges where life persisted. Yet life did more than just persist. It adapted and evolved. The Quaternary Ice Age saw the evolution of many species we associate with the Ice Age: woolly mammoths, saber-toothed cats, giant ground sloths, and cave bears. These were creatures perfectly adapted to a world of ice and cold, with thick fur coats and massive bodies designed to conserve heat. The Ice Ages also shaped early human evolution and migration. Land bridges connected several regions now separated by ocean, allowing our ancestors to spread across continents. Humans crossed the Bering Land Bridge to reach the Americas, island hopped across the exposed Indonesian archipelago to reach Australia, and followed ice-free corridors through massive ice sheets to colonize northern regions. But perhaps most remarkably, these weren't permanent changes. The growth and decay of these ice masses drove sea level fluctuations on the order of tens to over 100 meters on the time scales of hundreds to 10,000 years. Every 100,000 years or so, the vast ice sheets would begin to retreat, sea levels would rise, and Earth would transform from an ice world back to something resembling our modern climate. The most rapid and dramatic periods of sea level rise occurred during major deglaciations, when most northern hemisphere ice sheets disappeared and the Greenland and Antarctic ice sheets retreated to their present extents. These deglaciations could happen remarkably quickly. Massive ice sheets that took tens of thousands of years to build could collapse in just a few millennia. The birth of the modern ice ages marked Earth's entry into a new climate state, one characterized by dramatic oscillations between ice worlds and interglacial periods like our own. In a technical sense, we're still in an ice age called the Quaternary glaciation, which began about 2.6 million years ago. What we call our modern climate is actually a brief interglacial period in an ongoing ice age that shows no signs of ending. This realization puts our current climate in perspective. The warm, stable climate that enabled the rise of agriculture and civilization is not the normal state of our planet. It's a temporary respite in an ice age that has dominated Earth's climate for nearly 3 million years. Chapter 4. 21,000 years ago. 21,000 years ago, at the height of the last glacial maximum, Earth was a planet transformed. If an alien visitor had arrived during this period, they would have found a world barely recognizable as the blue marble we know today, a world where ice ruled supreme and the familiar geography of our modern planet was hidden beneath glaciers or lost beneath dramatically lowered seas. The last glacial maximum, much of the world was cold, dry, and inhospitable, with frequent storms and a dust-laden atmosphere. Some 8% of the planet's total surface was covered in ice, and sea levels were approximately 125 meters, 410 feet, lower than those of the present day. This represents the most recent time when ice sheets reached their maximum extent across Earth's surface. The scale of these ice sheets defies imagination. In North America, the Laurentide ice sheet stretched from coast to coast, covering virtually all of Canada, and extending deep into what is now the United States. According to the United States Geological Survey, permanent summer ice covered about 8% of Earth's surface and 25% of the land area during the last glacial maximum. Picture Chicago buried under ice over a mile thick, with glaciers extending as far south as modern-day Kansas and Missouri. The ice wasn't simply sitting there, it was a dynamic, flowing system that actively reshaped the continents. These glaciers moved like incredibly slow rivers, carving valleys, grinding down mountains, and transporting enormous quantities of rock and sediment. The Great Lakes themselves are scars left by these ice sheets, massive basins gouged out by the advancing and retreating ice. In Europe, the situation was equally dramatic. Most of Canada and northern Europe was covered with large ice sheets. The Fennoscandian ice sheet covered all of Scandinavia and extended across the Baltic Sea to cover much of northern Germany and Poland. Britain was completely buried under ice, with glaciers thick enough to overtop its highest mountains. The ice was so heavy that it depressed the solid Earth's crust by hundreds of meters. But the most visible impact was on the oceans themselves. The massive sheets of ice locked away water, lowering the sea level, exposing continental shelves, joining land masses together, and creating extensive coastal plains. The effect was dramatic. When all the ice was locked up in the ice sheets, global sea levels reached as much as 125 meters below present. This radical lowering of sea levels created a world map that would be unrecognizable to modern eyes. The English Channel didn't exist, it was a river valley. Another land bridge connected the island of Great Britain with the rest of continental Europe. You could have walked from London to Paris across dry land, following river valleys where the English Channel now flows. The changes were equally dramatic in other parts of the world. In Japan, the low water level made the Sea of Japan a lake, and a land bridge connected the region to the Asian mainland. The Yellow Sea, famous as a modern-day fishing location, was completely dry. The East China Sea was largely exposed land, with river systems cutting across what are now fishing grounds and shipping lanes. Perhaps most famously, northeastern Asia and northwestern North America were connected to each other by the Bering Land Bridge. This wasn't a narrow strip of land, it was a vast region called Beringia, hundreds of miles wide, that connected Siberia to Alaska. This land bridge would prove crucial for human history, as it provided the route by which early humans first entered the Americas. In the southern hemisphere, the changes were equally profound. Australia, Tasmania, and New Guinea were joined to form the continent Sahul. What we now call the Torres Strait was dry land, and early humans could walk from mainland Australia to New Guinea. The exposed continental shelves created vast new landscapes, grasslands and forests where the ocean floor now lies. The atmospheric conditions during the last glacial maximum were harsh beyond modern experience. The average global temperature about 21,000 years ago was about 6 degrees C, 11 degrees highs, colder than today. But this average masks the true severity of conditions in many regions. The US was a mix of ice sheets, alpine deserts, snow forests, semi-arid scrubland and temperate grasslands. The atmosphere itself was transformed. The dustiness of the atmosphere is a prominent feature in ice cores. Dust levels were as much as 20 to 25 times greater than they are in the present. This was probably due to a number of factors: reduced vegetation, stronger global winds, and less precipitation to clear dust from the atmosphere. The sky would have had a perpetual haze with dust storms far more severe than anything we see today. This dust came from the dramatically altered landscapes. The dry climate during the last ice age brought about the expansion of deserts and the disappearance of rivers. With so much water locked up in ice, precipitation patterns were completely different. Many regions that are lush today were barren wastelands, while other areas saw increased snowfall that fed the growing ice sheets. The ocean circulation was equally transformed. The ice sheets also changed the atmospheric circulation, causing the northern Pacific and Atlantic Oceans to cool and produce more clouds, which amplified the global cooling as the clouds reflected even more sunlight. The normal patterns of ocean currents that distribute heat around the planet were disrupted by the changed geography and the massive input of fresh meltwater. Interestingly, not all regions experience the same degree of cooling. The formation of an ice sheet or ice cap requires both prolonged cold and precipitation, snow. Hence, despite having temperatures similar to those of glaciated areas in North America and Europe, East Asia remained unglaciated except at higher elevations. The reason was atmospheric circulation. The ice sheets created high-pressure systems that blocked moisture from reaching Central Asia. Yet life persisted in this seemingly hostile world. Large mammals like woolly mammoths, woolly rhinoceros, and giant ground sloths were perfectly adapted to the cold conditions. Cave paintings from this period show early humans hunting these Ice Age giants across the frozen landscapes. Small populations of humans survived in refuges, ice-free areas like southern France, northern Spain, and parts of Eastern Europe. The tropics, while cooler than today, remained relatively habitable. In southeastern North America, between the southern Appalachian Mountains and the Atlantic Ocean, there was an enclave of unusually warm climate. These refuges preserved many species that would later recolonize the northern regions when the ice retreated. Chapter 5. When ice sheets collapsed. 15,000 years ago, something extraordinary began to happen. The massive ice sheets that had dominated Earth's landscape for over 100,000 years started to collapse. This was yet a gradual melting. It was one of the most dramatic climate transformations in Earth's recent history, a planetary-scale meltdown that would raise sea levels by over 400 feet and completely reshape the world map. The end of the last glacial maximum wasn't triggered by a single event, but by the same orbital cycles that had driven ice ages for millions of years. Over the past few million years, the glacial-interglacial cycles have been paced by periodic variations in the Earth's orbit via Milankovitch cycles. Around 20,000 years ago, these orbital cycles began favoring increased summer sunlight in the northern hemisphere, the key to melting the massive ice sheets. The deglaciation began slowly but accelerated dramatically. Between 19,000 and 15,000 years ago, the first major pulses of meltwater began flowing from the ice sheets into the oceans. But the real transformation began around 15,000 years ago, when the rate of melting accelerated exponentially. This period, known as Meltwater Pulse 1A, saw sea levels rise by over 20 meters, 65 feet, in just a few centuries, a rate of sea level rise that would be catastrophic if it happened today. The collapse of these ice sheets was a process almost beyond imagination. Picture the Laurentide ice sheet, which covered most of Canada and extended deep into the United States. At its peak, this single ice sheet contained enough water to lower global sea levels by over 80 meters. When it began to collapse, it didn't melt uniformly. Instead, it disintegrated in massive, catastrophic events. One of the most dramatic collapses occurred around 800 years ago, when the final remnants of the Laurentide ice sheet in Hudson Bay suddenly drained into the North Atlantic. This event, known as the 8.2 kiloyear event, dumped so much fresh water into the ocean that it temporarily shut down the Atlantic's circulation system, plunging the Northern Hemisphere back into near-glacial conditions for several centuries. The physics of ice sheet collapse reveals why these events were so dramatic. Ice sheets don't simply melt from the top down, they can collapse from the bottom up. As climate warmed, meltwater began flowing beneath the ice sheets, lubricating their bases and causing them to flow faster toward the sea. Marine ice sheets, those that extended into the ocean, were particularly vulnerable to catastrophic collapse. When a marine ice sheet's grounding line, the point where it lifts off the seafloor and begins to float, starts to retreat, the entire system can become unstable. The ice sheet essentially becomes an ice shelf, floating on the ocean and vulnerable to breaking apart. Once this process begins, it can become irreversible, leading to the complete collapse of the ice sheet in just a few hundred years. The melting ice had profound effects on ocean circulation. The massive amounts of fresh meltwater pouring into the oceans disrupted the normal patterns of ocean currents. The North Atlantic, in particular, became stratified, with fresh meltwater sitting on top of saltier, denser ocean water. This disrupted the formation of deep water masses that drive the global ocean circulation system. These disruptions had global consequences. The shutdown of Atlantic circulation could plunge Europe back into near-glacial conditions, even as ice sheets were collapsing elsewhere. The climate didn't warm steadily out of the Ice Age. Instead, it lurched between warm and cold periods, with dramatic climate swings happening in just decades. One of the most famous examples occurred around 12,900 years ago, when the Northern Hemisphere suddenly plunged back into glacial conditions for over 1,000 years. This period, known as the Younger Dryas, saw temperatures in the North Atlantic region drop by up to 10 degrees C in just a few decades. Glaciers that had been retreating began advancing again, and the climate became colder and more arid. The cause of the Younger Dryas remains debated, but most scientists believe it was triggered by a massive flood of meltwater from glacial Lake Agassiz, an enormous lake that formed as the Laurentide ice sheet retreated. When ice dams holding back this lake suddenly failed, they released more water than all the current Great Lakes combined directly into the North Atlantic, shutting down ocean circulation and triggering a return to Ice Age conditions. But the Younger Dryas was temporary. Around 11,700 years ago, the climate abruptly warmed again, ending the last glacial period and beginning our current interglacial, the Holocene. This transition was remarkably rapid. Temperatures in Greenland rose by up to 10 degrees C in just a few decades, and the change from glacial to interglacial conditions happened faster than modern climate change. The transformation of the landscape was equally dramatic. As the ice sheets retreated, they revealed landscapes that had been buried for over 100,000 years. But these weren't simply the old landscapes restored. The ice had completely reshaped the continents. The weight of the ice sheets had depressed the land by hundreds of meters, and as the ice melted, the land began to rebound upward in a process called post-glacial rebound. And this rebound is still happening today. Parts of Scandinavia and northern Canada are still rising by several centimeters per year as the land adjusts to the removal of the ice sheet's weight. Hudson Bay, in particular, is becoming shallower as the land around it continues to rise. Conversely, areas that were beyond the ice sheets, like the US East Coast, are still slowly sinking as the bulge of land that was pushed up around the ice sheets continues to subside. The rising seas transformed the world map. Land bridges that had connected continents for tens of thousands of years were gradually submerged. The Bering Land Bridge that had allowed humans and animals to migrate between Asia and North America was flooded around 11,000 years ago, separating the old and new worlds. Britain became an island again around 8,000 years ago when rising seas filled the English Channel. These changes weren't gradual, they often happened in dramatic steps. The final flooding of many land bridges occurred when ice dams holding back enormous lakes suddenly failed, releasing massive amounts of water in catastrophic floods. The Black Sea, for example, may have been suddenly flooded around 7,600 years ago when rising Mediterranean waters breached the natural dam at the Bosphorus, creating what some researchers believe inspired flood myths in many cultures. The biological impacts were equally profound. Many of the large mammals that had dominated the Ice Age world, woolly mammoths, giant ground sloths, saber-toothed cats, went extinct during this period. The exact causes are debated, but the combination of rapid climate change, habitat loss, and human hunting pressure proved fatal for many species that had survived previous glacial cycles. For the species that survived, the post-glacial world offered new opportunities. Forests spread northward, following the retreating ice. Species that had been confined to small refuges during the Ice Age were able to recolonize vast areas. The rapid environmental changes drove evolution and adaptation as species encountered new conditions and competitors. Human societies were transformed as well. The end of the Ice Age coincided with the development of agriculture in several parts of the world. The more stable, warmer climate of the Holocene allowed humans to develop farming and settle in permanent communities. The civilization we know today was built on the foundation of this post-glacial climate stability. The deglaciation that ended the last ice age demonstrates the incredible power of Earth's climate system to undergo rapid, dramatic changes. Ice sheets that seemed permanent and immutable could collapse in just a few centuries. Sea levels that had been stable for tens of thousands of years could rise by hundreds of feet in just a few millennia. This history provides sobering perspective on our current climate situation. The ice sheets that remain today in Greenland and Antarctica contain enough water to raise sea levels by over 70 meters if they were to melt completely. While such complete melting would take many centuries, the history of past deglaciations shows that ice sheets can collapse much faster than they form. The Great Meltdown that ended the last ice age reminds us that Earth's climate system has powerful feedback mechanisms that can accelerate change once tipping points are crossed. Understanding these past rapid climate changes is crucial for predicting how our climate might respond to the greenhouse gases we're adding to the atmosphere today. Chapter 6: Survival Against All Odds. In a world where ice stretched from pole to pole and temperatures plummeted to levels that would kill most modern life forms instantly, something extraordinary happened. Life not only survived, but in some cases, thrived. The story of how organisms endured Earth's most extreme climate events, from Snowball Earth to the last glacial maximum, reveals the incredible resilience and adaptability of life on our planet. During the Snowball Earth events of 700 million years ago, when the planet may have been frozen solid for millions of years, the survival of life seemed impossible. How could photosynthetic organisms, which need sunlight and liquid water, survive when Earth resembled a cosmic ice ball with ice sheets potentially a kilometer thick, covering the oceans? The answer lies in life's remarkable ability to find refuge in the most unlikely places. Recent research suggests that even during the worst of Snowball Earth, patches of open water may have existed. Some scientists believe that certain life forms did survive. Fossils from this period indicate that tiny organisms such as algae, which need sunlight and open water, lived both before and after the Snowball Earth. One possibility is that life persisted in geothermal areas. While the surface of the planet was frozen, volcanic activity continued beneath the ice, creating pockets of warmth. Hot springs and underwater volcanic vents could have provided oases of liquid water where primitive life forms could survive. After analyzing samples of phytoplanktons from different geothermal waters, scientists found that while these environments were hazardous to most life, some organisms could adapt through spontaneous mutations. Another refuge might have been the ice itself. Even in the harshest polar environments today, scientists find life thriving in seemingly impossible conditions. Some researchers suggest that the fossilized algae from Snowball Earth might have lived in tiny, shallow pools of freshwater atop glaciers. Today, such pools appear in polar ice sheets and provide a refuge for cold-adapted microbes. The chemistry of the frozen oceans also provided unexpected lifelines. Because about half of the ocean's water was frozen solid as ice, the remaining water would be twice as salty as it is today, lowering its freezing point. This hypersaline water could remain liquid even in extremely cold conditions, providing a habitat for specially adapted organisms. Some of the most compelling evidence for life's persistence comes from recent studies of sediments from the Marinoan Ice Age. Research examining a prehistoric layer of black shale from what would have been under the ocean during this Snowball Earth event found fossils of algae as well as nitrogen compounds that suggest the waters were oxygenated. This indicates that photosynthetic life continued even during the depths of global glaciation. The survival strategies developed during these extreme events had lasting impacts on evolution. Some scientists think that the conditions of Snowball Earth changed life in the oceans, leading to the rise of more complex algae, large cells, over cyanobacteria, small cells. The extreme selective pressure of global glaciation may have favored larger, more complex cells that could store more energy and survive longer periods without optimal conditions. When the ice ages of the more recent Quaternary period began, life had already learned many of the tricks necessary for survival in frozen worlds. But the challenges were different. Instead of a permanently frozen planet, organisms had to adapt to cyclical changes between glacial and interglacial periods. The mammals that evolved during the Pleistocene ice ages became masters of cold weather survival. Woolly mammoths developed thick, multi-layered coats that could insulate them in temperatures far below freezing. Their rounded ears and short tails minimized heat loss, while their massive bodies helped them retain warmth. These giants could survive in environments where modern elephants would freeze to death in hours. Cave bears developed different strategies, using their intelligence and behavioral adaptations to survive. They learned to hibernate through the worst of winter, slowing their metabolism and living off stored fat for months at a time. Their caves provided protection not just from the cold, but from the fierce storms that characterized glacial climates. Even plants developed remarkable adaptations to ice age conditions. During glacial periods, many tree species survived in small refugia, isolated pockets of suitable habitat where they could persist through tens of thousands of years of harsh conditions. These refugia were often in protected valleys, near geothermal features, or in regions where local geography created slightly warmer microclimates. The most successful plants were those that could rapidly recolonize new territory when conditions improved. Birch trees, for example, became masters of the post-glacial world because they could quickly spread across newly ice-free territory and establish forests in harsh conditions where other trees couldn't survive. But perhaps the most remarkable survival story involves our own species. Early humans not only survived the last glacial maximum, but used it as an opportunity to spread across the globe. The land bridges created by lowered sea levels allowed humans to reach Australia, the Americas, and remote islands that would be inaccessible when ice ages ended. Human survival required unprecedented innovation. Archaeological evidence shows that Ice Age humans developed sophisticated technologies for surviving in harsh conditions. They learned to make fitted clothing from animal skins, construct insulated shelters, and hunt the massive Ice Age fauna that shared their frozen world. Perhaps most importantly, they developed complex social structures that allowed knowledge to be passed down through generations. The techniques for surviving in Ice Age conditions, which animals to hunt, which plants were edible, how to track game across frozen landscapes, became part of human cultural knowledge that ensured survival even when individual communities faced catastrophe. The archaeological record reveals human ingenuity in the face of extreme climate challenges. Cave paintings from the Ice Age show early humans hunting mammoths and other Ice Age giants, suggesting they had developed sophisticated hunting strategies for taking down prey much larger than themselves. Evidence of controlled fire shows they could maintain warmth and cook food even in the harshest conditions. Ice Age humans also demonstrated remarkable mobility. Genetic evidence suggests that small populations could survive for thousands of years in isolated refuges, then rapidly expand and recolonize vast territories when conditions improved. This boom and bust cycle of human populations mirrored the advance and retreat of the ice sheets themselves. The development of language during this period may have been crucial for survival. The ability to communicate complex information about weather patterns, animal behavior, and survival techniques would have given human groups enormous advantages in the challenging Ice Age environment. Marine life developed equally sophisticated survival strategies. During glacial periods, many ocean species migrated to warmer waters near the equator or found refuge in areas where warm currents created pockets of suitable habitat. Some species developed the ability to enter dormant states during the harshest periods, slowing their metabolism and waiting for better conditions. Microscopic life in the oceans showed perhaps the greatest adaptability. Plankton species that form the base of marine food webs could rapidly evolve to adapt to changing ocean chemistry and temperature. Their short generation times allowed them to evolve new survival strategies in just a few years rather than the thousands of years required for larger organisms. The story of survival during Earth's great freezes reveals several crucial principles. First, life's diversity is its greatest strength. Having many different species with different survival strategies ensures that some will make it through even the most extreme conditions. Second, the ability to find and exploit refugia, small pockets of suitable habitat, can allow species to survive catastrophic environmental changes. Perhaps most importantly, these survival stories show that life is far more resilient than we might expect. Even conditions that seem incompatible with life, frozen oceans, dust-laden atmospheres, temperatures far below anything we experience today, can be survived by organisms that develop appropriate adaptations. However, these survival stories also carry warnings. While life as a whole survived even the most extreme ice ages, individual species often didn't. The fossil record shows that each glacial cycle caused numerous extinctions, particularly among species that couldn't adapt quickly enough to changing conditions or couldn't find suitable refugia. The end of the last ice age saw the extinction of most large mammals, woolly mammoths, giant ground sloths, saber-toothed cats, and many others. These species had survived multiple glacial cycles but couldn't adapt to the rapid changes that occurred as the Ice Age ended and human populations expanded. Today, as we face rapid climate change in the opposite direction, the lessons from Ice Age survival are more relevant than ever. Understanding how life survived past climate extremes can help us predict which species are most vulnerable to current changes and develop strategies to protect biodiversity in our rapidly changing world. The organisms that survived Earth's great freezes were those that were most adaptable, most mobile, and best able to exploit new opportunities. As our planet faces its next great climate transformation, these same qualities may determine which species thrive in the world we're creating. Chapter 7. How Ice Ages Change the Seas Beneath the Frozen Surface of Ice Age. Earth lay a hidden world in constant motion, the vast circulation systems of the world's oceans. These massive currents, often called the global ocean conveyor belt, were not just affected by ice ages. They were fundamental drivers of the climate changes that created and ended glacial periods. Understanding how ice ages transformed ocean circulation reveals one of the most powerful and sensitive components of Earth's climate system. Today's ocean circulation is often thought of as a kind of conveyor belt, with downwelling occurring in the North Atlantic and upwelling in the Indian and Pacific Oceans and around Antarctica. This circulation system transports heat from the equator toward the poles, helping to moderate global climate. But during ice ages, this delicate system was repeatedly disrupted, reorganized, and sometimes shut down entirely. The disruption began with the ice sheets themselves. The massive sheets of ice locked away water, lowering the sea level, exposing continental shelves, joining land masses together, and creating extensive coastal plains. But the effects went far deeper than just changing coastlines. As ice sheets grew, they fundamentally altered the density and salinity of seawater, the very properties that drive ocean circulation. When vast amounts of water were locked up in ice sheets, The remaining ocean water became more saline, saltier than today's oceans. This hypersaline water was denser and behaved differently from modern seawater. The increased salinity changed where and how water masses sank and rose, completely reorganizing the three-dimensional structure of ocean circulation. Even more dramatically, when ice sheets began to melt, they poured enormous volumes of fresh water into the oceans. This fresh water was much less dense than normal seawater, so it would float on top of the saltier water below, creating a stratified ocean that prevented normal circulation patterns from operating. One of the most dramatic examples occurred during the collapse of the North American ice sheets. Around 8,200 years ago, the final remnants of the Laurentide ice sheet in Hudson Bay suddenly drained into the North Atlantic. This event dumped so much fresh water into the ocean that it temporarily shut down the Atlantic's circulation system, plunging the Northern Hemisphere back into near-glacial conditions for several centuries. But this wasn't an isolated event. Throughout the ice ages, the ocean circulation system repeatedly switched between different modes of operation. During glacial periods, the circulation was often weaker and organized differently than today. The formation of deep water masses, the engine that drives global circulation, occurred in different locations and at different rates. Evidence for these changes comes from deep-sea sediment cores that preserve chemical signatures of past ocean conditions. These cores reveal that during peak glacial periods, the ocean circulation was dramatically different from today. The North Atlantic deep water, which today forms a major component of global circulation, was either much weaker or formed in completely different locations. The Pacific Ocean shows equally dramatic changes. During glacial periods, abyssal Pacific overturning was weaker during the LGM than in the present day, although it was temporarily stronger during some intervals of ice sheet retreat. The normal patterns of upwelling and downwelling that bring nutrients to the surface and oxygen to the deep ocean were altered, creating very different conditions for marine life. Perhaps most dramatically, evidence suggests that during some periods, the normal direction of ocean circulation actually reversed. Instead of warm surface waters flowing northward in the Atlantic and cold deep waters flowing southward, the circulation temporarily flipped, with profound consequences for global climate. These circulation changes had cascading effects throughout the climate system. When the North Atlantic circulation shut down, it prevented warm tropical waters from reaching northern Europe and the Arctic. The result was rapid cooling. Temperatures could drop by 10 degrees or more in just a few decades, causing glaciers that had been retreating to advance again. The tropical regions were affected as well. Changes in ocean circulation altered the position and strength of the tropical rain belts, causing droughts in some regions and increased precipitation in others. The El Niño Southern Oscillation, ENSO, was strong during the LGM, but its patterns were different from today, affecting weather patterns across the Pacific Basin. The ice sheets themselves became part of the ocean circulation system in unexpected ways. As they extended into the ocean, they created massive floating ice shelves that could carve enormous icebergs. These icebergs, some the size of small countries, would drift across the oceans, melting as they went and dumping fresh water far from their source. Evidence for these iceberg armadas comes from deep-sea sediments that contain ice-rafted debris, rocks and sediments that could only have been transported by floating ice. During certain periods, these debris layers show that massive numbers of icebergs were crossing the Atlantic, creating what scientists call Heinrich events, after the researcher who first identified them. Heinrich events represent some of the most dramatic examples of how ice sheets could disrupt ocean circulation. Every few thousand years, the massive ice sheets surrounding the North Atlantic would suddenly release enormous numbers of icebergs. These iceberg armadas would flood the North Atlantic with fresh water, shutting down circulation and causing rapid climate changes across the Northern Hemisphere. The timing of Heinrich events wasn't random. They occurred during specific phases of the glacial cycles, suggesting they were triggered by internal instabilities in the ice sheets themselves. As ice sheets grew larger and thicker, they became increasingly unstable. Eventually, they would reach a tipping point where large sections would suddenly break away and slide into the ocean. These events show how different components of the climate system, ice sheets, oceans, and atmosphere, are intimately connected. Changes in one component can trigger rapid responses in others, leading to cascading changes throughout the global climate system. The recovery from these circulation shutdowns was often as dramatic as their onset. When the icebergs melted and the input of fresh water decreased, normal circulation patterns could resume surprisingly quickly. Temperatures that had taken decades to drop could recover in just a few years, demonstrating the potential for rapid climate transitions. But not all circulation changes were temporary. Some represented permanent reorganizations of the ocean system that persisted for thousands of years. The Antarctic Circumpolar Current, which today isolates Antarctica from warm tropical waters, only formed when Australia separated from Antarctica around 45 million years ago. This circulation change was one of the key factors that allowed ice sheets to form on Antarctica in the first place. Similarly, the closing of the Isthmus of Panama around 3 million years ago fundamentally altered global ocean circulation by preventing water exchange between the Atlantic and Pacific. This change helped strengthen the Gulf Stream and may have been crucial for triggering the ice ages of the past few million years. Modern studies of ocean circulation during ice ages use sophisticated computer models to simulate how the oceans behaved under different climate conditions. These models reveal that the ocean circulation system has multiple stable states, different configurations that can persist for long periods but can switch between each other relatively rapidly when conditions change. The implications are sobering for our current climate situation. The same ocean circulation system that was repeatedly disrupted during ice ages continues to operate today and remains sensitive to changes in fresh water input and temperature. Current climate change is already affecting ocean circulation in measurable ways. The Greenland ice sheet is currently losing mass at an accelerating rate, adding fresh water to the North Atlantic. Some studies suggest that the Atlantic circulation system is already weakening in response to this fresh water input, potentially affecting weather patterns across Europe and North America. Understanding how ocean circulation responded to past climate changes is crucial for predicting how it might respond to future changes. The paleoclimate record shows that circulation changes can happen much faster than previously thought, and can trigger rapid climate transitions that affect the entire planet. The ocean circulation system acts as both a stabilizer and an amplifier of climate change. Under normal conditions, it helps moderate climate by transporting heat around the globe. But when pushed beyond certain thresholds, it can amplify climate changes and trigger rapid transitions between different climate states. The Ice Age record reveals that our planet's ocean circulation system is far more dynamic and sensitive than we might expect from observing it during our relatively stable modern climate. The conveyor belt that helps regulate our current climate has repeatedly stalled, reversed, and reorganized throughout Earth's history, often triggering dramatic climate changes in the process. As we continue to alter our planet's climate system through greenhouse gas emissions, the lessons from Ice Age ocean circulation become increasingly relevant. The same mechanisms that repeatedly reorganized ocean circulation during past climate changes are still operating today, reminding us that our climate system has the potential for surprises that could reshape our world in ways we're only beginning to understand. Chapter 8. Giants of the Frozen World. Imagine stepping into a time machine and emerging 20,000 years ago during the last glacial maximum. The world that greets you would be populated by creatures so extraordinary they seem mythical, giants adapted to a frozen world that our modern fauna could never survive. This was the age of the megafauna, when Earth was home to the largest land animals that have walked the planet, since the dinosaurs. The undisputed kings of this frozen realm were the woolly mammoths. These massive relatives of modern elephants stood up to 11 feet tall at the shoulder and weighed as much as 6 tons. But size alone didn't make them remarkable. It was their incredible adaptations to Ice Age conditions that made them true marvels of evolution. A woolly mammoth was essentially a living fortress against the cold. Their thick, multi-layered coat consisted of an outer layer of guard hairs up to 3 feet long, covering a dense undercoat that provided insulation equivalent to the best modern Arctic gear. Beneath this fur lay a layer of fat up to 4 inches thick, creating a biological thermal barrier that allowed them to maintain body temperature in conditions that would kill modern elephants in hours. Every aspect of their anatomy was fine-tuned for cold survival. Their ears were small and rounded, unlike the large, fan-like ears of African elephants, to minimize heat loss. Their trunks were shorter and more muscular, reducing surface area exposed to the cold. Even their blood contained natural antifreeze compounds that prevented ice crystals from forming in their circulatory system. These giants weren't just surviving in the Ice Age world, they were thriving. Woolly mammoths ranged across vast areas of North America, Europe, and Asia, from Alaska to Spain. They lived in herds that could number in the hundreds, creating some of the largest aggregations of large mammals ever recorded. The frozen permafrost of Siberia has preserved some specimens so perfectly that scientists have been able to study their DNA and even examine their last meals. But mammoths weren't the only titans of the Ice Age. The woolly rhinoceros was equally impressive, a massive beast covered in thick fur with a horn that could reach 4 feet in length. Unlike modern rhinos, which live in warm climates, these creatures were perfectly adapted to the frozen steppes, using their massive horns to sweep snow aside and reach the vegetation underneath. Even more impressive was the giant ground sloth, particularly Megatherium, which could reach 20 feet in length and weigh as much as 8 tons, larger than most elephants. These weren't the slow tree-dwelling sloths we know today, but massive terrestrial giants that could rear up on their hind legs to reach vegetation 15 feet above the ground. Some species had claws over a foot long, which they used both for digging and defense. The predators of this world were equally formidable. The cave lion was 25% larger than modern lions, with males weighing up to 800 pounds. These weren't the savanna hunters we know today. They were adapted to hunting in the harsh conditions of Ice Age, Europe, and Asia, preying on mammoth calves, horses, and reindeer across the frozen landscapes. Perhaps the most iconic Ice Age predator was the saber-toothed cat, particularly Smilodon. With canine teeth that could reach 7 inches in length, these cats were the ultimate ambush predators. But those massive teeth weren't just for show. They were precision instruments designed to deliver a killing bite to the throat of large prey. Saber-toothed cats had incredibly powerful neck and shoulder muscles that allowed them to drive those teeth deep into their victims. The cave bear represents one of the most successful large mammals of the Ice Age. These giants, which could weigh over 1,000 pounds, were primarily vegetarian despite their fearsome appearance. They developed behavioral adaptations that allowed them to survive harsh winters by hibernating in caves for months at a time. Archaeological evidence shows they shared these caves with early humans, leading to encounters that undoubtedly inspired many legends. But the Ice Age bestiary extended far beyond these famous giants. The Irish elk, despite its name, was found across Europe and Asia, and was actually a giant deer with antlers that spanned up to 12 feet, the largest antlers of any deer that ever lived. These massive antlers were so large that scientists initially thought they must have been evolutionary mistakes that led to the species' extinction, but modern research shows they were actually displays of fitness that helped males compete for mates. In the Americas, the short-faced bear was the largest terrestrial carnivore of the Ice Age. Standing 8 feet tall on its hind legs and weighing up to 1,500 pounds, it was 50% larger than modern polar bears. Its long legs suggest it was built for running rather than the slower gait of modern bears. Imagine a grizzly bear the size of a small horse that could chase down prey across the frozen steppes. The diversity of Ice Age horses was remarkable. These weren't the domesticated horses we know today, but wild species adapted to different Ice Age environments. Some were tiny, pony-sized creatures that lived in harsh mountain environments. Others were large, robust animals that grazed on the mammoth steppes alongside their giant companions. Even the smaller animals of the Ice Age world were extraordinary. The cave hyena was larger and more robust than modern hyenas, adapted to hunting in packs across the frozen landscapes of Europe. Giant beavers the size of black bears built dams in the rivers of North America. Terror birds in South America stood over 6 feet tall and had beaks capable of crushing skulls. What made this abundance of giants possible was the unique ecosystem of the Ice Age world. The mammoth steppe that stretched across northern continents was one of the most productive ecosystems Earth has ever seen. This wasn't the sparse tundra we see in the Arctic today, but a rich grassland that could support enormous herds of large herbivores. The key was the climate itself. The cold, dry conditions of the Ice Age created an ecosystem without modern parallels. The lack of trees meant that more energy went into grasses and herbs that could support large herbivores. The dry climate prevented the formation of peat bogs and other wetlands that characterize modern Arctic regions, maintaining productive grasslands at high latitudes. This ecosystem supported animal populations that defy modern imagination. Some estimates suggest that the biomass of large mammals during the Ice Age was 10 times greater than today. The Siberian steppes alone may have supported millions of mammoths, along with comparable numbers of woolly rhinos, horses, and other large herbivores. But this world of giants was doomed. As the Ice Age ended and the climate warmed, the mammoth steppe ecosystem began to collapse. Rising temperatures led to the expansion of forests and wetlands that couldn't support large herbivore populations. The productive grasslands that had sustained the Ice Age giants were replaced by modern ecosystems with much lower carrying capacity. The timing of extinctions closely follows the end of the Ice Age. Most large mammals went extinct between 15,000 and 10,000 years ago, coinciding with rapid climate change and the expansion of human populations. The exact causes remain debated: climate change, human hunting, or a combination of both likely contributed to the extinctions. Some species managed to survive in refugia, small populations that persisted in isolated locations with suitable habitat. Woolly mammoths survived on Wrangel Island in the Arctic Ocean until just 4,000 years ago, when the Egyptian pyramids were already ancient. But these were remnant populations, shadows of the vast herds that once roamed the Ice Age world. The loss of Ice Age megafauna represents one of the most dramatic biodiversity losses in Earth's recent history. In just a few thousand years, ecosystems that had existed for hundreds of thousands of years were completely transformed. The largest land animals disappeared, along with the ecosystems that supported them. Today, the largest land mammals are elephants, which are smaller than many Ice Age species and exist in small, fragmented populations. The productive ecosystems that once supported millions of large mammals have been replaced by systems dominated by much smaller animals. Yet the legacy of Ice Age giants continues to fascinate us. Preserved in permafrost caves and fossil deposits around the world, these creatures provide a window into a world where life took on forms almost beyond imagination. They remind us that Earth's ecosystems have supported levels of biodiversity and biomass far greater than what we see today. The Ice Age bestiary also provides crucial insights into how ecosystems respond to rapid climate change. The extinction of the megafauna shows how quickly established ecosystems can collapse when environmental conditions change rapidly. As we face our own period of rapid climate change, the fate of Ice Age giants provides sobering lessons about the vulnerability of large species to environmental transformation. The giants of the frozen world were products of their time, perfectly adapted to conditions that no longer exist. Their rise and fall illustrates both the incredible adaptability of life and its vulnerability to rapid environmental change. They remind us that the natural world is capable of supporting diversity and abundance beyond our modern experience, but also that such richness can be lost with startling speed when conditions change. Chapter 9. Human Stories from the Frozen World. In the depths of the last glacial maximum, when vast ice sheets stretched across continents and sea levels had dropped by over 400 feet, small bands of humans not only survived, but embarked on some of the greatest adventures in our species' history. These weren't the comfortable, settled societies we know from later periods. These were nomadic hunters and gatherers whose lives were defined by constant movement, incredible hardship, and remarkable ingenuity in the face of a hostile world. Picture a typical day for these Ice Age survivors. The temperature might be 30 degrees below freezing, with winds howling across the treeless steppes. Snow and ice stretched to the horizon, broken only by the occasional boulder or the distant shape of a mammoth herd. These humans had no permanent shelters, no agriculture, no metal tools, just stone, bone, wood, and animal hide, along with the most powerful survival tool ever evolved, the human brain. Archaeological evidence reveals that Ice Age humans developed technologies that wouldn't be out of place in a modern survival manual. They learned to make fitted clothing from animal skins that provided insulation comparable to modern Arctic gear. Needle-making technology allowed them to create tailored garments with multiple layers, waterproof outer shells made from seal or mammoth hide, insulating middle layers of fur, and soft inner garments against the skin. Their shelters were marvels of engineering adapted to available materials. In areas where wood was scarce, they built homes from mammoth bones and tusks, covering them with hides and sod to create surprisingly effective insulation. Some of these bone houses required the remains of dozens of mammoths and could shelter extended families through the harsh winter months. But perhaps most remarkably, Ice Age humans used the harsh conditions to their advantage. The permafrost became a natural freezer, allowing them to store meat from large kills for months. Archaeological sites show evidence of massive communal hunts, where entire herds of mammoth or bison were driven into traps, providing enough food to sustain communities through the long winter months. The social implications of this lifestyle were profound. Survival required unprecedented cooperation. Knowledge about weather patterns, animal behavior, tool-making, and hunting strategies had to be shared and passed down through generations. The development of complex language during this period may have been driven by the need to communicate detailed information about survival in harsh conditions. Evidence of this sophisticated knowledge system comes from cave paintings created during the Ice Age. The caves of Lascaux, Chauvet, and Altamira contain some of the most beautiful and accurate depictions of Ice Age animals ever created. But these weren't just art, they were educational tools, teaching materials that helped pass on crucial knowledge about the anatomy, behavior, and hunting strategies for the giant creatures that shared their world. The Chauvet cave paintings, created over 30,000 years ago, show intimate knowledge of animal behavior that could only come from close observation. The artists knew how cave lions hunted, how mammoths moved in herds, how horses behaved in different seasons. This wasn't just artistic expression, it was a survival manual painted on cave walls. Ice Age humans also demonstrated remarkable mobility and adaptability. Genetic evidence suggests that small populations could survive for thousands of years in isolated refuges, then rapidly expand and recolonize vast territories when conditions improved. This boom and bust cycle of human populations mirrored the advance and retreat of the ice sheets themselves. Perhaps most dramatically, Ice Age humans used the changed geography of the glacial world to spread to every habitable continent. The land bridges created by lowered sea levels became highways for human migration. Around 15,000 years ago, humans crossed the Bering Land Bridge to enter the Americas for the first time. This wasn't a simple crossing, it was an epic journey across a landscape unlike anything that exists today. The Bering Land Bridge wasn't just a narrow strip of land, it was a vast region called Beringia, hundreds of miles wide, with its own unique ecosystem. Early Americans didn't just walk across and keep going, they lived in Beringia for thousands of years, adapting to its unique conditions before eventually moving south into the Americas. When they did move south, they encountered a landscape filled with giant animals that had never seen humans. Massive ground sloths, giant beavers, American cheetahs, and short-faced bears populated a continent that was radically different from today. Within just a few thousand years, most of these giant animals were extinct, though the exact role of human hunting versus climate change remains debated. Similar stories of Ice Age exploration played out around the world. Humans reached Australia at least 50,000 years ago when sea levels were lower, but the journey still required sophisticated boat-building technology and navigation skills. They had to cross at least 60 miles of open ocean during some of the most challenging climate conditions Earth has experienced. In Europe, Ice Age humans survived in refuges in southern France, northern Spain, and parts of Eastern Europe. These weren't just random hiding places, they were carefully chosen locations that provided access to water, shelter from the worst weather, and proximity to animal migration routes. The famous cave sites like Altamira and Lascaux were part of larger landscape use patterns that allowed humans to thrive in Ice Age Europe. The tool technology developed by Ice Age humans was remarkably sophisticated. They created composite tools with multiple components, spear points hafted to wooden shafts, atlatls that increased throwing power, and even early forms of specialized hunting equipment for different types of prey. Some tools were so well made that they remained sharp and functional for decades. But technology alone couldn't ensure survival. Social organization was equally crucial. Ice Age humans lived in small bands that regularly met with other groups to exchange information, trade materials, and find marriage partners. These gatherings were crucial for maintaining genetic diversity and sharing survival knowledge across wide regions. Evidence for these social networks comes from archaeological sites that contain materials from hundreds of miles away. High-quality stone for tools, shells for decoration, and amber for trade. Ice Age humans maintained contact networks that spanned continents, allowing innovations and information to spread rapidly across vast distances. The end of the Ice Age brought both opportunities and challenges for human societies. As the climate warmed and sea levels rose, many of the land bridges that had allowed human migration were flooded. The Bering Land Bridge that had connected Asia and the Americas disappeared around 11,000 years ago, separating Old and New World populations for thousands of years. Rising seas also flooded coastal areas where many human settlements were located. Since Ice Age, humans often lived near coastlines to exploit marine resources, many archaeological sites from this period are now underwater. This represents a significant loss of information about how our ancestors lived during this crucial period. But warming climate also brought new opportunities. The retreat of ice sheets opened vast new territories for human settlement. Forests spread northward, providing new resources and hunting opportunities. The more stable climate of the post-glacial period allowed for innovations like agriculture and permanent settlements. Some researchers argue that the challenging conditions of the Ice Age were crucial for human evolution. The need to survive in harsh, variable conditions may have selected for the intelligence, adaptability, and social cooperation that characterize our species. The Ice Age forged humans into the ultimate generalists, capable of surviving in almost any environment through technology and social organization. The genetic legacy of Ice Age populations continues to shape human diversity today. Different human populations show genetic adaptations to the environments their ancestors survived in during the Ice Age. Arctic peoples have genetic adaptations for metabolizing fat and surviving in extreme cold. Highland populations have adaptations for low oxygen conditions that may trace back to Ice Age refugees in mountainous regions. Perhaps most importantly, Ice Age humans developed the cultural and technological foundations that would later allow for civilization, the complex language, sophisticated tool traditions, artistic expression, and social organization that characterized Ice Age societies provided the platform for all subsequent human development. The cave paintings of Ice Age artists represent some of humanity's first great artistic achievements, but they also demonstrate cognitive abilities, symbolic thinking, planning, and communication that are fundamental to human culture. The hunters who brought down mammoths with stone-tipped spears were using the same problem-solving abilities that would later build cities and send humans to the moon. Today, as we face rapid climate change, the story of Ice Age humans provides both inspiration and practical lessons. Our ancestors survived climate changes more dramatic than anything predicted for our future, but they did so at enormous cost in terms of population size and geographic range. The flexibility and adaptability that allowed Ice Age humans to survive may be our greatest assets in facing the climate challenges ahead. The human stories from the frozen world remind us that our species has always been defined by its ability to adapt to changing conditions. But they also show that survival often comes at a cost, and that the stable climate conditions that allowed for the development of agriculture and civilization are precious and not to be taken for granted. Chapter 10. When the Ice Melted. Imagine witnessing one of the most dramatic transformations in Earth's recent history, the end of the last glacial maximum and the birth of the modern world. Over the span of just 10,000 years, a period that seems long to us, but is merely a blink in geological time, ice sheets that had dominated continents for over 100,000 years melted away sea levels, rose by over 400 feet, and the entire geography of our planet was rewritten. This wasn't a gradual, uniform warming. It was a chaotic, sometimes violent transformation marked by rapid climate swings, catastrophic floods, and the collapse of ecosystems that had remained stable for tens of thousands of years. The story of deglaciation reveals just how quickly our planet's climate system can reorganize itself, with lessons that resonate powerfully in our current era of rapid climate change. The transformation began around 19,000 years ago, triggered by the same orbital cycles that had driven ice ages for millions of years. Changes in Earth's orbit around the Sun increased summer sunlight in the northern hemisphere, beginning to tip the energy balance away from ice accumulation toward melting. But what started as a subtle shift in solar energy would cascade into one of the most dramatic climate changes in Earth's history. The first signs were subtle: slightly more melting during summer months, small increases in the discharge from glacial rivers. But these small changes triggered powerful feedback mechanisms that accelerated the warming. As ice melted and exposed darker land surfaces, less sunlight was reflected back to space, and more was absorbed, causing additional warming. This ice albedo feedback would prove to be one of the most powerful amplifiers of climate change. The melting wasn't uniform across the globe. Different ice sheets responded to warming at different rates and in different ways. Mountain glaciers, with their smaller size and exposure to warming air, began retreating first. The massive continental ice sheets were more resistant to change initially, but when they began to collapse, they did so with startling speed. Between 19,000 and 15,000 years ago, the rate of melting accelerated dramatically. This period saw the first major pulses of meltwater flowing from the ice sheets into the oceans. Rivers that had been frozen for millennia began flowing again, carving new channels and creating vast lakes where ice had once stood. The collapse of ice-dammed lakes created some of the most spectacular events of the deglaciation. As ice sheets retreated, they often left behind natural dams that trapped enormous volumes of meltwater. When these ice dams failed, they released floods of almost unimaginable scale. The Missoula floods in the Pacific Northwest released more water than all current rivers combined, carving the channeled scablands of Washington state in just a few days. Lake Agassiz, formed by meltwater from the retreating Laurentide ice sheet, was larger than all the current Great Lakes combined. When ice dams containing this enormous lake suddenly failed around 8,200 years ago, they released a volume of fresh water into the North Atlantic equivalent to all the water in Lake Superior. This catastrophic flood was so massive it temporarily shut down ocean circulation and plunged the Northern Hemisphere back into near-glacial conditions for several centuries. But perhaps the most dramatic aspect of deglaciation was how rapidly it could occur. Ice sheets that had taken tens of thousands of years to build could collapse in just a few millennia. The physics of ice sheet collapse helps explain this asymmetry. While ice accumulation is limited by the rate of snowfall, ice loss can accelerate rapidly once melting begins. Marine ice sheets, those that extended into the ocean, were particularly vulnerable to rapid collapse. As warming progressed, the edges of these ice sheets began to float, becoming ice shelves vulnerable to breakup. Once the grounding line, the point where ice transitions from resting on land to floating on water, began to retreat, the entire ice sheet could become unstable. The collapse of marine ice sheets created massive armadas of icebergs that drifted across the oceans, melting as they went and dumping fresh water far from their source. Evidence for these iceberg invasions comes from deep-sea sediments containing ice-rafted debris, rocks and sediments that could only have been transported by floating ice. These Heinrich events, named after the scientist who first identified them, represent some of the most dramatic examples of rapid ice sheet collapse. During these events, the ocean around the ice sheets became choked with icebergs, some the size of small countries. The fresh water from these melting bergs was enough to disrupt ocean circulation across entire ocean basins. The effects on global climate were profound and sometimes paradoxical. While the overall trend was toward warming, the massive influx of fresh water from melting ice could trigger rapid cooling in some regions. The most famous example is the Younger Dryas, a period around 12,900 years ago, when temperatures in the North Atlantic region dropped by up to 10° in just a few decades. The Younger Dryas demonstrates how rapidly Earth's climate system can change direction. Just as the world seemed to be warming steadily out of the Ice Age, a massive flood of meltwater from Lake Agassiz disrupted Atlantic circulation and plunged much of the Northern Hemisphere back into near-glacial conditions. Glaciers that had been retreating began advancing again, and the climate became colder and more arid. But the Younger Dryas was temporary. Around 11,700 years ago, the climate abruptly warmed again, ending the last glacial period and beginning our current interglacial, the Holocene. This transition was remarkably rapid. Temperatures in Greenland rose by up to 10°C in just a few decades, demonstrating the potential for dramatic climate transitions. The transformation of landscapes during deglaciation was equally dramatic. As ice sheets retreated, they revealed landscapes that had been buried for over 100,000 years. But these weren't simply the old landscapes restored. The ice had completely reshaped the continents. Massive glaciers had carved valleys, ground down mountains, and transported enormous quantities of rock and sediment. The weight of the ice sheets had also depressed the land by hundreds of meters. As the ice melted, the land began to rebound upward in a process called post-glacial rebound that continues today. Parts of Scandinavia and northern Canada are still rising by several centimeters per year, as the land adjusts to the removal of the ice sheet's weight. The rising seas of deglaciation transformed the world map as dramatically as the melting ice transformed the continents. Land bridges that had connected continents for tens of thousands of years were gradually submerged. The Bering Land Bridge that had allowed humans and animals to migrate between Asia and North America was flooded around 11,000 years ago, separating the old and new worlds. Britain became an island again around 8,000 years ago when rising seas filled what had been a river valley during the Ice Age, creating the English Channel. The North Sea, which had been largely dry land where early humans hunted reindeer and mammoth, became the shallow sea we know today. These changes weren't always gradual. Some land bridges were flooded catastrophically when ice dams failed, or when rising seas breached natural barriers. The Black Sea, for example, may have been suddenly flooded around 7,600 years ago when rising Mediterranean waters breached the natural dam at the Bosphorus, an event that some researchers believe inspired flood myths in many cultures. The biological impacts of deglaciation were equally profound. Many of the large mammals that had dominated the Ice Age world went extinct during this period. Woolly mammoths, giant ground sloths, saber-toothed cats, and dozens of other species disappeared forever. The exact causes remain debated, but the combination of rapid climate change, habitat loss, and human hunting pressure proved fatal for many species. For the species that survived, the post-glacial world offered both opportunities and challenges. Forests spread northward, following the retreating ice and providing new habitats for woodland species. But the productive mammoth steppes that had supported enormous herds of large herbivores were replaced by less productive tundra and forest ecosystems. Human societies were transformed as well. The more stable, warmer climate of the Holocene allowed for innovations that had been impossible during the Ice Age. Agriculture developed independently in several parts of the world during the early Holocene, providing the foundation for settled communities and eventually civilization. But the transition wasn't uniformly beneficial for early humans. The flooding of coastal areas where many communities lived forced massive relocations. Many archaeological sites from the Ice Age are now underwater on continental shelves, representing a significant loss of information about this crucial period in human history. The deglaciation also created new migration routes as ice-free corridors opened through the retreating ice sheets. These corridors allowed both animals and humans to colonize regions that had been inaccessible during the height of the Ice Age. The initial peopling of the interior of North America may have occurred through such corridors as the Cordilleran and Laurentide ice sheets separated. The end of the Ice Age marks one of the most dramatic climate transitions in Earth's recent history. In just 10,000 years, our planet transformed from an ice world to the warm, stable climate that has characterized most of human civilization. This transformation demonstrates both the incredible dynamics of Earth's climate system and its potential for rapid, dramatic change. The speed and magnitude of Ice Age deglaciation provides sobering perspective on our current climate situation. The ice sheets that remain today in Greenland and Antarctica contain enough water to raise sea levels by over 70 meters if they were to melt completely. While such complete melting would take many centuries, the history of past deglaciations shows that ice sheets can collapse much faster than they form. Understanding how ice sheets collapsed in the past is crucial for predicting how they might respond to current warming. The same feedback mechanisms that accelerated ice loss during past deglaciations, ice albedo feedbacks, marine ice sheet instabilities, and meltwater effects on ocean circulation, are operating today and could lead to faster ice loss than current models predict. The great transformation that ended the last ice age reminds us that Earth's climate system has powerful feedback mechanisms that can accelerate change once tipping points are crossed. The relatively stable climate that has allowed human civilization to flourish is not the normal state of our planet. It's a brief interglacial period in an ongoing ice age, and understanding how such periods begin and end is crucial for predicting our climate future. Chapter 11: Ice Ages and the Future. As we stand at the threshold of a new climate era, one shaped by human activities rather than natural cycles, the lessons from Earth's frozen past have never been more relevant. The ice ages that have dominated our planet's recent climate history offer profound insights into how our climate system responds to changing atmospheric composition, how quickly dramatic changes can occur, and what we might expect as we continue to alter the composition of our atmosphere. The orbital cycles that have driven ice ages for the past 3 million years continue to operate today. According to these natural cycles, Earth should gradually be cooling toward the next ice age over the coming thousands of years. Some scientists predicted that without human influence, the next glacial period might begin in about 1,500 years. However, the massive amounts of greenhouse gases we've added to the atmosphere have fundamentally altered this trajectory. Current industrial activities have warmed the climate considerably and may in fact delay the next ice age by 50,000, 100,000 years. This represents one of the most dramatic examples of human influence on the planetary climate system. We have effectively cancelled the next ice age. The greenhouse gases we've released have overwhelmed the natural cooling trend that should be leading toward glaciation. But the lessons from ice ages extend far beyond questions of timing. Perhaps most importantly, the Ice Age record reveals that our climate system has multiple stable states and can transition between them with startling rapidity. The same climate system that produced the stable, warm conditions of the past 10,000 years also produced Snowball Earth events, abrupt transitions like the Younger Dryas, and dramatic oscillations between glacial and interglacial states. This inherent instability means that our climate system has the potential for surprises, rapid transitions to new states that could occur much faster than gradual warming trends might suggest. The paleoclimate record shows that many of the most dramatic climate changes in Earth's history happened not gradually over centuries, but rapidly over decades or even years. One of the most sobering lessons comes from studying how ice sheets have responded to past warming. During previous deglaciations, ice sheets that had seemed stable for tens of thousands of years collapsed with remarkable speed when climate tipping points were crossed. The Laurentide ice sheet, which covered most of Canada during the last ice age, disappeared almost entirely in just a few thousand years. Today, the Greenland and West Antarctic ice sheets show signs of accelerating mass loss that parallel the early stages of past ice sheet collapses. The same feedback mechanisms that accelerated ice loss during past deglaciations, such as ice albedo feedbacks, where darker surfaces absorb more heat than white ice, are operating today and could lead to faster ice loss than current models predict. The West Antarctic ice sheet is particularly vulnerable because much of it rests on bedrock that is below sea level. Like the marine ice sheets that collapsed rapidly during past deglaciations, the West Antarctic ice sheet could become unstable if its grounding line begins to retreat. Some scientists believe this process may already be underway, potentially committing us to several meters of sea level rise over the coming centuries. The Ice Age record also reveals how sensitive ocean circulation is to changes in freshwater input and temperature. Past climate changes repeatedly disrupted the ocean circulation system, sometimes shutting it down entirely and triggering rapid climate changes across the globe. Current observations suggest that the Atlantic circulation system is already weakening in response to fresh water from melting Greenland ice and changing precipitation patterns. A shutdown of Atlantic circulation would have profound consequences for climate, particularly in Europe and Eastern North America. The paleoclimate record shows that such shutdowns can happen rapidly and can persist for centuries or even millennia. While climate models suggest that a complete shutdown is unlikely in the near future, the risk increases with continued warming and ice loss. But perhaps the most important lesson from ice ages concerns the relationship between atmospheric CO2 and climate. Ice core records spanning the past 800,000 years show that atmospheric CO2 levels have fluctuated between roughly 180 parts per million during glacial periods and 300 ppm during interglacials. These natural variations were closely coupled with ice age cycles. Low CO2 helped maintain glacial conditions, while higher CO2 contributed to interglacial warming. Today, atmospheric CO2 levels have risen to over 420 ppm, far above anything seen in the ice core record. We are conducting an unprecedented experiment with our planet's atmosphere, pushing CO2 levels into territory not seen for millions of years. The paleoclimate record from earlier periods, when CO2 levels were similarly high, suggests that such concentrations are associated with much warmer climates and significantly higher sea levels. During the Pliocene epoch, about 3 million years ago, when CO2 levels were similar to today's, global temperatures were 3 to 4 degrees Celsius warmer than present, and sea levels were 15 to 25 meters higher. While it took thousands of years for the full climate response to unfold during the Pliocene, this period provides a glimpse of where our current trajectory might lead. The Ice Age record also reveals the crucial role of feedback mechanisms in amplifying climate changes. Small changes in solar energy distribution due to orbital cycles were amplified by feedbacks involving ice sheets, vegetation, ocean circulation, and atmospheric composition. These same feedback mechanisms operate today and could amplify the warming from greenhouse gas emissions in ways that are difficult to predict. One of the most concerning feedback mechanisms involves the Arctic. As Arctic sea ice melts, it exposes dark ocean water that absorbs much more solar energy than white ice. This ice albedo feedback is already contributing to rapid Arctic warming and could accelerate as more ice is lost. The paleoclimate record shows that this feedback mechanism has contributed to rapid climate transitions in the past. Another potential feedback involves permafrost, the permanently frozen ground that underlies much of the Arctic. As temperatures warm, permafrost begins to thaw, potentially releasing large amounts of stored carbon as CO2 and methane. While this process is only beginning today, the paleoclimate record suggests that permafrost feedbacks could become significant if warming continues. The Ice Age record also provides perspective on the rate of current climate change. While past climate changes were often dramatic, they typically occurred over timescales of centuries to millennia. The current rate of warming is happening much faster than most natural climate changes, giving ecosystems and human societies less time to adapt. However, the paleoclimate record does contain examples of very rapid climate changes that occurred over decades or even years. The onset of the Younger Dryas, for example, saw temperatures drop by up to 10 degrees Celsius in just a few decades. These rapid changes were typically triggered by specific events, such as the sudden drainage of glacial lakes, but they demonstrate that the climate system is capable of very rapid transitions. For human societies, the lessons from ice ages are both sobering and inspiring. Our ancestors survived climate changes more dramatic than anything predicted for our future, demonstrating the adaptability and resilience of our species. But they did so at enormous cost in terms of population size, geographic range, and cultural complexity. The Ice Age archaeological record shows that human populations repeatedly crashed and recovered in response to climate changes. Small groups survived in refugia during harsh periods, then rapidly expanded when conditions improved. This boom and bust pattern characterized human demographics throughout the Ice Ages. Today's human population and technological society are fundamentally different from Ice Age hunter-gatherers. We have capabilities our ancestors couldn't imagine: the ability to predict climate changes, adapt our environment to changing conditions, and potentially even engineer solutions to climate problems. But we also have vulnerabilities they didn't face: complex, interdependent systems that could be disrupted by climate changes, and a population of nearly 8 billion people who depend on stable climate conditions for food production. The Ice Age record suggests that the stable climate of the past 10,000 years, the period during which agriculture developed and civilization arose, is actually unusual in Earth's recent history. Most of the past few million years have been characterized by much more variable climate conditions. This raises important questions about the long-term sustainability of our current agricultural and economic systems in a more variable climate. But the Ice Age record also reveals the incredible resilience and adaptability of life on Earth. Even during the most extreme climate events, Snowball Earth episodes that may have frozen the entire planet, life not only survived, but evolved and diversified. This resilience provides hope that life, including human life, can adapt to changing climate conditions. The key insight from Ice Ages may be that preparation and adaptability are crucial for surviving climate changes. Ice Age humans survived by developing technologies and social systems that allowed them to adapt quickly to changing conditions. Today, we need similar adaptability, technologies that can help us adapt to climate change, social systems that can respond quickly to new challenges, and economic systems that can function under different climate conditions. Understanding Ice Ages also helps us appreciate the value of climate stability. The warm, stable climate of the Holocene allowed for the development of agriculture, permanent settlements, and complex societies. As we alter our climate system, we risk losing this stability and returning to the more variable conditions that characterize most of Ice Age history. Perhaps most importantly, the Ice Age record reminds us that climate change is not just about gradually warmer temperatures. It's about the potential for rapid transitions to fundamentally different climate states. The same planet that has given us 10,000 years of climate stability has also produced Snowball Earth events, abrupt warming episodes, and dramatic oscillations between different climate modes. As we continue to add greenhouse gases to the atmosphere, we are not just causing gradual warming, we are fundamentally altering the behavior of the climate system that has shaped the evolution of life on Earth for millions of years. The lessons from Ice Ages suggest that this system is capable of dramatic surprises, and that preparation for rapid climate transitions may be as important as adaptation to gradual change. The frozen past provides a powerful reminder that our climate system is dynamic, sensitive, and capable of dramatic changes. As we face the climate challenges of the future, the lessons from Earth's Ice Ages will be crucial guides for understanding what changes are possible, how quickly they can occur, and how life, including human life, might adapt to a rapidly changing world. As we reach the end of our journey through Earth's frozen epochs, we return to the questions that opened our exploration. What forces could freeze entire oceans? How did life survive these planetary deep freezes? And what can these ancient Ice Ages tell us about Earth's future? The answers reveal a planet far more dynamic and dramatic than our everyday experience suggests. From the incomprehensible extremes of Snowball Earth, where our entire planet may have resembled a cosmic ice ball, to the cyclical advance and retreat of ice sheets during the Quaternary glaciation, Earth's climate system has repeatedly demonstrated its capacity for transformation on scales that dwarf human experience. We've seen how relatively small changes, the collision of continents, shifts in ocean circulation, variations in Earth's orbit, can trigger cascading changes that reshape the entire planet. The same feedback mechanisms that once froze oceans solid and later caused massive ice sheets to collapse in just a few millennia continue to operate today, reminding us that our climate system retains its potential for dramatic surprises. Perhaps most remarkably, we've discovered that life not only survived these extreme conditions but often thrived and evolved in response to them. From the microscopic organisms that may have persisted in hidden refuges during Snowball Earth to the magnificent Ice Age giants that dominated the frozen landscapes of the Pleistocene, life has repeatedly demonstrated its incredible resilience and adaptability. The human story is equally inspiring and sobering. Our ancestors survived climate changes more dramatic than anything predicted for our future, spreading across the globe and developing the technologies and social systems that would eventually lead to civilization. But they did so as small, mobile populations that could adapt quickly to changing conditions, very different from our modern world of billions of people dependent on stable climate for food production and economic systems. Today, as we face rapid climate change driven by our own activities, the lessons from Earth's frozen past have never been more relevant. We've learned that our climate system can transition between dramatically different states much faster than previously thought, that ice sheets can collapse rapidly once tipping points are crossed, and that the stable climate of the past 10,000 years is actually unusual in Earth's recent history. The ice ages remind us that we live on a dynamic planet capable of dramatic transformation. They provide both warnings about the potential for rapid change and inspiration from life's incredible ability to adapt and survive. Most importantly, they remind us that the warm, stable climate that enabled human civilization is precious and not to be taken for granted. Understanding Earth's frozen past does not just tell us where we've been, it helps us prepare for where we are going in our rapidly changing world. The frozen epochs don't end there. Just 21,000 years ago, during the last glacial maximum, some 8% of the planet's total surface was covered in ice, and sea levels were approximately 125 meters lower than those of the present day. Massive ice sheets stretched across continents, locking away so much water that entire regions we consider oceanic today were dry land. What forces could freeze entire oceans? How did life survive these planetary deep freezes? And what can these ancient ice ages tell us about Earth's future climate? Today, we're embarking on a journey through Earth's most dramatic climate transformations, from the incomprehensible Snowball Earth events to the recent ice ages that shaped the world humans inherited.